Welcome to a presentation of the Newton's fourth PPA1530 Compact Power Analyser. Here we're going to demonstrate some of the standard features on the instrument. We will also illustrate how standby power measurements, and some particular problems associated with that application, will be solved by this product. We have a load already connected, so we can switch on the instrument and see the power-up routine. First, the display will show instrument details while carrying out a self-check, and then automatically detect the input frequency and optimum ranges for the input being measured. Immediately, you see the power in terms of total values, fundamental values plus DC power, and phase angles. This is the standard mode of the instrument, and the display shows some zoom functions which may be of particular interest. While we're on the screen, we will illustrate that you can zoom in any parameter you want to see in greater detail. And if we stop at this point, you can see that there is a red block around the selected items. This red block can be moved with cursor keys, so you can zoom into any function you want. We will leave it at the standard watts, volts, amps and frequency, as these are often of greatest interest in power electronic applications. We are presently connected to a 50 Hz sinusoidal waveform, and we can establish the nature of voltage in current waveforms by moving to the scope mode at the press of a single button. As you can see, there is a sine wave voltage and a sine wave current, which most power analyzers can measure with perfect ease. If, however, we want to look at harmonics and distortion, we move on to look into different modes. There is an RMS button, which will show all the RMS components plus the DC, AC, peak, surge, rectified mean and crest factor of voltage plus current and frequency. Harmonic Analysis, again in a single button press, will show the harmonic distortion of the voltage plus the current, plus the primary harmonic components. Another button press gives a table where we see absolute fundamental, absolute harmonics, and then percentages of the harmonics of the fundamental for volts and current, or a bar graph. While here we have a small graph because the distortion is low. We can zoom in the graph and see harmonics in more detail. We have the real-time harmonics in yellow and the peaks in red. If we now go back to the oscilloscope mode, we want to illustrate a particular problem associated with standby power, and that is the low-duty cycle pulses of current. This is where a standby power supply will take a trickle current followed by periodic pulses of current to charge the input stage during standby mode. This is a particular problem for power analyzers because it causes a problem for frequency detection and ranging, and the power will tend to pulse. So if we go to the power mode, we can illustrate this by increasing the instrument acquisition speed using the acquisition menu where we select fast. And here we can see the measurement speed increase. If we now adjust the pulse rate to a lower duty cycle, we can see that the power is changing between a nominal low level and then the pulse level. This creates a challenge for switch mode power supply analysis with low duty cycle power consumption and is usually solved by integration over time. However, Newton's fourth have a solution to this, which is a standby power mode. If we select the standby power mode in the acquisition menu, we see that the power screen changes slightly with the addition of a second frequency. At the bottom of the screen, we now see a 10 Hz frequency, which is the period of the pulse frequency, and this period will change depending upon the frequency of the pulse. So if I change the frequency from 1 in 5 of the 50 Hz cycle to 1 in 20, it can be seen that the measured pulse frequency changes from a 10 Hz period to a 2.5 Hz period. I can flick back to 1 in 5, and all the time the instrument is synchronized to the voltage and the current. You will also notice that the power remains completely stable, even when I switch to a low-duty cycle. And we have steady 729 milliwatts power instead of 500 milliwatts, followed by large pulses. We therefore have a solution to switch mode power analysis of low-duty standby in one instrument, with no external shunts and with no smoothing required. Thank you for watching. We hope you found this presentation useful.